The first talk will be Alberto Carrassi, who will be talking to us about machine learning in geophysical data assimilation.
Well, good afternoon, everyone, and of course, thank you to the organizers. It's very nice. It's very nice to be here. Do you hear me? So if I no, okay, I will try to speak a bit louder. Yeah, I can speak loud. I can speak louder. I think I can. So this. Okay, we'll start anyway. So this is a talk which I wanted to tell a story about some of the work that we have been doing in the last 2.5 years, where we attempted to see in which way we could combine data simulation and machine learning. Now, it is true that I must admit, as part of the data simulation community, because it seems that we have one, that at the beginning, where of this explosion of machine learning entered into play, we were a bit jealous because a lot of things that they do, we did it since long. So at the beginning, I was saying this to Valerio and Michael before. One of the things that they've been doing in the last year sometimes was having a sort of little dictionary in which I translated terminology from the very fancy terminology that we have now, for instance, backpropagator, which is the adjoint, so on and so forth. This is not what I'm going to do today, because of course there is a lot that we can gain and from using machine learning in a way that I would love to make clear in this talk. So I think what we are experiencing now in data simulation is like a sort of transition from being a discipline that, at least in geosciences, has been strongly model-driven to somehow a bit more data-driven. The reason why is because historically, you know, geosciences and numerical weather prediction in particular is one of the areas of physics in which we have relatively good models, and we want to use those good models. And also, it is very well known that the availability of such good models has been pivotal in the success of data simulation in the past. The typical images of how well the information from the data-dense North America propagate in the extratropic tour into the ocean was a proof of how well the model was able to fill that gap. So to propagate information from the observed to the unobserved area. At the same time, however, we are not so naive. We use those models being aware that those models are not perfect. And in fact, there is a long literature on data simulation for imperfect model, as well as a literature on trying to use data simulation to improve such a model in some way. And this is what I think this part of the plot illustrates. Yeah, I'm sorry. This is what this part of the plot want to illustrate, which in fact the data simulation is indeed the merge of these two different sources of information, which are both very important. On the other hand, of course, you know, we are living this explosion of machine learning tools. They have been incredibly powerful. The reason for this is, in my opinion, not anything new, mathematically speaking, but it relies largely on the capability to deal a large amount of data, and which is also connected to the capability of work on GPU, architecture, and so on and so forth. So in machine learning, the problem is slightly different in the sense that usually the classical machine learning problem is the one of using data in order to learn something about the process that the data speak about. And this is illustrated in this part of the figure in which you can see the hardware goes uniquely from the observation toward the model situation. So this is the picture, and I think I have synthesized a bit at high level what the difference is. And now I will try to explain a bit more what, in my opinion, are the different areas of application and the way how we combine them. To do so, I made this two-dimensional panel here, in which you have on the x-axis what I call the goodness of the physical model, or what we believe to be, from no model at all into a perfect model, in passing through an imperfect model, where by imperfection we can include many different things, of course, biases, such as even a structural difference in the equation that we use to describe the process. On the y-axis, on the other hand, we have the goodness of the data, and again, our belief in them, which of course started from noisy, sparse data. Sparse is intended to be both time and space, all the way to the ideal situation of having a perfect network of observation. In this two-dimensional panel, I will try to locate what I think are grosso modo the area of application and the realms of machine learning and data simulation. Machine learning is already here, and you can see that you can place the pure machine learning, classical machine learning problem, which is the one of emulating hidden dynamics. And this is located in this area here because this is the problem in which if you use the data that you have at disposal by thinking that they are perfect and they are complete, and you want to use them to reconstruct a model that you don't have. At the same time, well, and you probably know that there is a lot of work, and this is particularly important in climate science, in which we don't do this because this doesn't make sense, because we have good models, we want to use them. So we use machine learning to complement such models. Typically, we can use machine learning to learn some parameterization or to correct the model error. That's why I place this here. But importantly, they are still located they are still working under the assumption that we have a complete and perfect data set. What about, so this is just, I mean, you know, it's very difficult, it's literally very difficult to follow all of the literature that appears. So this is just a short example of that. Okay? So I apologize for those who have been excluded. Similarly, I can place data simulation in this two-dimensional plot in which you have, you know, the classical situation in which, you know, data simulation in geoscience has been very typically used for noisy and sparse data. And we have a data simulation assuming a perfect model. This is what it is often referred in our domain as a strong constraint, in the sense that you believe that your model is perfect and you can then you can strongly constrain your solution on it. But as I said before, we have also done a lot of data simulation with imperfect model for state and parameter estimation. This is also often referred in variational context as a weak constraint, in the sense that, again, the model is this time not followed perfectly. Now, there is also something that we have done recently in which we have used data simulation, in particular weak constraint variational simulation, in order to do the job which is usually done by machine learning. This has been published in this paper a few years ago. And but there is a caveat, however, which is important. The caveat is that in order to solve for that problem, we need to know the structure of the equation. So in that specific case, we need to know which type of ODE we had at disposal. Now, this talk will be about 3 different parts, which I hope to be able to go through. The first is what I call the sort of non-intrusive approach to machine learning. This is the work which is primarily done by Daniel Hayers, who is one of my students who is in the and it's placed in this area of this two-dimensional plot because in this case, we are not touching our model. We are thinking, we have a model that we want to use, and we use machine learning as a supplement to that, to do some task. In particular, we will use that to make the task of estimating the local Lyapunov exponent of the system. In the second part of my talk, I will specifically talk about the combination of data simulation and machine learning for 2 different goals. The first will be the goal of building a complete emulator of hidden dynamics. So I wanted to reproduce the dynamics which is giving rise to the data. And in the final part, I will use this combination of data simulation and machine learning in a way that I will hopefully clarify in a moment, to infer some model parameterization. So we are not longer substituting the model completely. Okay, so on the first part, there is no data simulation here. We were motivated by more or less the same, grosso modo, more or less the same idea that motivated the work by Yuman Chen, Gus Foster was presented yesterday. The idea here was, can we substitute the full computational cost of computing the spectrum of Lyapunov exponent by training a machine learning algorithm? This is what we have been doing here. This is the result in this archive paper here. And we play with 2 very well known models, 3-dimensional model, Rosler on the left and Lorentz 63 on the right. And this refer to different machine learning methods. And these are the time series of the local Lyapunov exponent, the first, the second, and the third for the 2 different models, the target, so what we wanted to reproduce given in blue, and the prediction in orange. What you can see already visually is that while the prediction of the last exponent is very good, it's relatively good also the prediction of the first. On the other hand, we have a number of spots of pure prediction of the neutral node. Remember that the second exponent is associated to be tangent to the flow in this 3-dimensional system. In particular, what we saw is that this is an example of the Hershey score, the deviation from the Hershey score, which is a measure of the accuracy of our prediction. again for the two system, Rosler and Lorentz, and for the first, second, and third exponent. And the color are proportional to the error that we are committing. In particular, the yellow stands for the larger prediction, the bluish for the lowest prediction error. What these plots say is that the larger accuracy, the larger prediction error that we commit with our machine learning algorithm are usually associated with area of strong heterogeneity of the local attractor. In particular, it's like what this testifies that the mapping that we are trying to learn from the state of the trajectory into the space of the Lyapunov exponent, which is highly sensitive to the so can be highly sensitive to each initial condition in certain area of the attractor, is more difficult to deliver. This is about the second part and the third part now, and here is where really the data simulation comes into play, and so I will be able to give more mathematical detail if you want, but this is the general scheme we are dealing with. So we work on a sort of iterative steps in which we initialize our model which can be just a parametric model which is given by a machine learning algorithm. Then we provide a data simulation step. So we do a data simulation step to assimilate the noisy and sparse data. The output of the data simulation step is the analysis field. And this analysis field is then used to train again and so to re-optimize the parameter of the machine learning model. And then the system is repeated. This schematic process here. DL stands for deep learning. Sorry, Marcus. Deep learning. It's for deep learning. This schematic here is mathematically known as the descent algorithm. It's a coordinate descent. So essentially what we are solving is an optimization problem where the cost function is formulated both in terms of the parameter we want to estimate, A, and the set of initial condition. Obviously, this problem is very difficult to be solved because there is an interdependency between X and A. So what we are essentially doing here is that we're using two different family of algorithms, but mathematically speaking, we are just doing the following. We fix one while we minimize on the other, and then we go forward. This is referred to coordinate descent algorithm. As I say, this schematic will be more or less with some differences, which I will clarify, used for two different goals: building a full model of the observed process and infer the model error and build another physical data-driven model. This is, again, more specifically what we are doing. We are working, so this is the mathematical formulation of the problem. This is the emulator. This is the model that we want to emulate, that is approximated by a machine learning model, which is parameterized by the parameter W here, plus an error. We use, for the data simulation part, the finite size ensemble Cannon filter. The reason for that is because it is a method which implicitly computes the inflation, which is needed in ensemble method. And the goal here, as I say, is we will stop the converge at some point, and the goal is to create an emulator, a full model of the observed process. A bit on the specific here. So this is essentially the cost function that is at the core of the optimization problem of the machine learning. This is the one that will be minimized. Now, two key things here. The first is that the target here will be given by the output of the data simulation method. The second is that the weight, so the normalization factor here, that covariance matrix here, which usually is time independent, it will become time dependent because we are using an ensemble method. For those of you familiar with that, ensemble method provide a sort of automatic way to have the associated error covariance together with the state. So at each new step, we will have an updated ensemble-based covariance matrix that is used in the minimization of the machine learning part. The results are something we have result with different models, but this is what I will show today. Comes by the Lorentz 96. It's a model that everybody knows. I think it describes the evolution of the atmospheric variable around the circle of equal latitude. It is driven by an external forcing, and you also have dissipation and advection. So this plot represents the power spectrum density. So it's like a sort of measure, statistically speaking, of how good our emulator is of the system that we have used to produce the data, the noisy data. You see that, of course, there is the true model here, which is just what we obtain by taking a long time series of the free model run. And then we have two curves, one for after one cycle, and then the final one, the surrogate that we are able to create at convergence. So you see that after one cycle, some frequencies are powered, so the initial peak, which is the reason why usually the periodic signal are learned first. And then a convergence surrogate model produces the spectrum quite well up to this point. It doesn't work so well when for the higher frequency, but this is, I know this is a typical problem for all optimization methods. A byproduct of this analysis, the fact that we were able to compute this power spectrum density is because we were able to run our surrogate model for a long time. And this is not obvious because when you create a surrogate model based on machine learning method, there are often probable stability when you run the model for free. Similarly, we are computing here the spectrum of this time the asymptotic spectrum of the Lyapunov exponent. Again, we are using this spectrum as a metric of the goodness of our emulator. This is now the amplitude of the Lyapunov spectrum here, and of the Lyapunov exponent here, and the indexes of them. So you can see that the true is blue and the surrogate is in orange. You see that we do a very good job for estimating the unstable part of the spectrum. This doesn't happen to be the case in the stable part, and this is primarily because we commit an error in the natural mode. So again, this seems reminiscent of the problem that I mentioned in the first part of the talk in relation to the Daniel work, in which we had a problem also in estimating properly the natural mode. As a matter of fact, there are a series of work that probably you know that have been done by Patak et al. In the Edward Hott group, in which they were using a completely different approach. They were using full data, and they were using reservoir computing, but again, they also found the same issue on properly estimating the neutral mode. Interesting, however, the fact that we are able to estimate the unstable part of the spectrum is somehow a good sign, because at least we are able to compute properly the rate at which we lose information in the surrogate as compared to the underlying model. This is a classical plot, that Holm-Waller plot that you may see in many machine learning papers, in which you have essentially the evolution of the true, the evolution of the surrogate. So you have the time in the x-axis in the Lyapunov unit, and you have in color the amplitude. Of course, you cannot discern any difference here, but when you take the difference between the two, you see that it's quite wide up to approximately 2 Lyapunov time, which is approximately the length at which the accuracy of our prediction is reasonable. Finally, we work on what is probably the most common and relevant problem, which is the one of, at least in climate science, which is the one of reproducing only a portion of the process of play. Because we want to keep for as much as possible the model that we have used, because they are based on physical equation. So here the problem is slightly different. What we want to do here is that we have a physical model, which I indicated by the suffix phi here, and we wanted to correct this model by adding a portion of the correction, which is what comes by the unresolved scale, which our model is not able to resolve. So the goal here will be the one of using this combined data simulation and machine learning method to estimate this part. So this exactly comes to say that we wanted to derive a data-driven parameterization. Now, obviously, there is already a big hypothesis here, which has a lot of consequence from the point of view of the optimization problem, which is the fact that we are assuming that the correction is addictive, and there is no reason why this should be the case in the general frame. But as I say, if you include the correction here, this is a classical problem in data simulation as well. When you make your model error depending on the state, that creates then an interdependency when you resolve the problem, which is far more difficult. So let's see the result. So first of all, a bit on the points. We are using a coupled atmosphere-ocean model, which I will describe in the next slide. And because of the couple between two systems of different scale, we already decided to use coupled data simulation, in particular what we call in the area strongly coupled data simulation. Let me just explain briefly what it is. It is when whatever the observations are located, no matter in the ocean or in the atmosphere, for instance, those observations are used to inform also the other part of the domain. So, for instance, data taken in the ocean will infer, if there is a correlation which tells you to do so, they will also infer the atmosphere and vice versa. I will make clear later why this has been important in our result. Now, what are we doing here is the following. We use we run strongly coupled data simulation using the physical model, the one that we have at disposal. And we collect the analysis increment, which is essentially the difference between the analysis and the prior, or the mean of the prior, which is often referred to as the background. So this analysis increment will now become the target, which is the model error that we want to correct. So what is the underlying hypothesis here? Well, the underlying hypothesis here is that, which is of course questionable, is that the analysis increment is a good proxy of the model error. This is not obviously the case in general. It will be more and more correct as long as we reduce the initial condition error. So more and more we reduce the initial condition error, and more the analysis increment will only be done by a portion coming from model error, which is what we intend to correct in this problem. We have, by the way, this concept of using model errors or using analysis increment as a proxy of the model error has been also largely used in data simulation for long, and this is something that I did with Stefan in 2011 in a different context. But now, coming back to our problem, we wanted now to minimize the loss function of the machine learning component. The parameter are called theta, sorry, they were called W a few slides ago. And here the target is analysis increment, okay? Once this is constructed, once we have estimated our correction coming from machine learning, we will have now a new model done by the sum of two components, the original physical model plus the correction that we have constructed. This is the model that I anticipated before. It's a model that I'm sure many of you know already. It's a model that has been developed in the group of Stefan van Nissem since 2016 or even before, probably even before. And it's a model which is constituted from, at least there are several versions of this model, and I think it is also now available a version in Python with more features, including a different type of coupling than the one that I'm using in this experiment. But in any case, what I'm using here is the model which describes the atmosphere and the ocean the atmosphere is in such a layer, while the ocean is a shallow water ocean layer. A key advantage of this model in the practical sense is that it is resolved in spectral mode, that you can almost arbitrarily play with the length of that expansion, so making your model bigger or smaller, okay? This is just a snapshot of the attractor in three of the dimension. The experiment in this case are run with a model of dimension 36, but doesn't matter, here I'm just showing three of those variables. And you can see that the model oscillates by a situation where you have a sort of slow regime into a situation in which the regime is more, say, unstable. We implemented strongly coupled ensemble-Kalman filtering, which has been specifically designed for this model, and in which we observe both the atmospheric stream function and the ocean temperature. Okay, so how the experiment are designed? In this experiment, our truth is done by formulation of our model, which use 20 modes for the atmosphere, 8 modes for the ocean, and which makes up a total of a state vector dimension of 56. The truncated model, so the physical model that we assume to have at disposal, will be done by a truncated version of it, in which we truncated 10 of 10 atmospheric modes, and which make a dimension of 36. So the truncated model is missing 20 higher order atmospheric variable. And this is a more technical point here, as opposed to the previous experiment in which we have used convolutional neural network. Because the model is expressed in spectral coordinate, we don't have any more of the notion of distance here. So we cannot use the locality, which is typically powerful elements of the convolutional neural network. And it turns out that the best machine learning algorithm that, at least among those that we have tested, was the multi-layer perceptor. This is a table which summarizes a bit of the result. We have the root mean square error of the forecast at different lead time. Is 2 here for the oceanic variable. It's 1 day for atmospheric variable. This is just because there is a big temporal scale difference between the two compartments. This is the error of the original truncated model, and this is the error that we get after the model is corrected by the parameterization based on the DEA machine learning approach. So of what we see as the hybrid model are superior scale than the truncated one. But what is nice here to observe is that the improvement is larger for the ocean that is fully observed. So the only way this improvement can come from is from the data that has been taken in the atmosphere. And that is why I think this is a proof, this is an indication of the role of the couple data simulation here. A different picture of the result can be taken by this comparison of the model attractor on two plane. This is the second component of the oceanic stream function, the first component of the atmospheric stream function. This is the true model. This is the truncated model. You see the populated area of the model attractor that are not even present in the reality. And this is what our hybrid model does. Of course, it's not perfect, but you see that it has largely corrected this bunch of that was present in the original model. So this is essentially the last result that I will show. So what are we doing now? We are trying to translate this idea of a model-driven data simulation and the data-driven data simulation in a recent project we started a year ago, which is called SASIP, which is a project in which we are applying this idea to describing the CI's dynamics and thermodynamics. The beauty and the difficulty of the problem comes by what this picture like this shows. This is a picture of the marginalized zone, in which you can clearly see that the sea ice has a it's alternate fluid with a solid-like system with a fragmentation of granular head cases here. So it's very complicated and it presents a lot of challenge from the point of view of data simulation and from the point of view of parameterizing process, which are then important in climate system. This is the goal of this project we are running now. And just to promote a bit the project and to promote the work of the people who are actually doing the work, one of the things that we're working now is what is called, it belongs a bit more to the category of model driven, which is what you have seen, hopefully you have seen yesterday in the poster by Ivo, in which we are trying this time to tailor the data simulation setup specifically to the dynamical core of the model. So in a way, we are again model driven. This is a bit opposed and in parallel to what Simon Driscoll has been doing. And again, this was presented in the poster yesterday, where we are using machine learning at the moment, pure machine learning, to describe some of the physical process, in particular the thermodynamical process which took place in the vertical, which are very important because they determine the melting of the sea ice, and so the creation of this melt pond, which then have a lot of effect in the albedo. All of these two lines of research, hopefully next year, will be merged together when we will deal with real data. And so we'll have to face the fact that we only have noisy and sparse data, and therefore we presume that is the context in which we need a combination with data simulation to make machine learning work in practice. So these are a bit of a conclusion. We show three ways on how using machine learning in geophysical DA and forecasting enterprise. One is to supplement the physical model. The second is to infer parameterization of a resolve or poorly known process. And the third one is to fully emulate any of the dynamics. I just realized now that I present them in different orders, so I don't want to confuse them there. So we studied the potential for machine learning to estimate the local Lyapunov exponent. The result have been quite positive in those models. I didn't say, I can tell now for sincerity that they are not translating so successfully in a higher dimension model. We are trying to understand why, and also in a way reformulating the problem from a regression into a classification. This is not what I'm talking about. You can ask them instead if you are more interested. And then we have developed a combined data simulation and machine learning method, where data simulation is instrumental, in particular because data simulation allows to include a state-dependent estimate of uncertainty, which is not usually classical machine learning method. Note that any data simulation can be plugged in, but if you plug an ensemble-based method, then you also have the associated uncertainty. Finally, these are the reference that I've used, that a bit of advertisement. There is this special collection that we are doing on quarterly on combined data simulation and machine learning, and also take advantage to say that there will be some opening position next year in Bologna on data simulation and machine learning, if any of you is interested or can spread information. Thank you.
Thank you. We've got time for a couple of questions. Yes.
In the case of the data-driven model you developed, you compute the spectra of the
using a breadth vector approach.
Yeah. So, what I can see is that it's well, your data-driven model is highly dissipative as compared to the other one, right?
Oh, yeah,
So,
exactly.
Could you relate that to some, let's say, dynamical structure of your model?
We didn't, but that's a good suggestion. What we have interpreted to be the case is that, which is probably wrong, is that if you look at that, there is really a shift which took place here. So my impression is that the error that you see in this part of the spectrum is originated by the error that you have done here. So I think that the way how the exponents are really ordered to each other, stay proximal the chain, but it is this error that then propagate down. But you're probably right. We didn't think further on that. We actually developed a discussion also with other colleagues around how difficult it was to compute a neutral node. But we didn't really think about the stable one and why there would be the problem per se. There was another question.
Another question over there.
Yes, so I hope you don't mind if I play the devil's advocate a bit, because
No,
you know, it's essentially a family meeting. Right? So if you look at the let's say the research goals that you also listed in the conclusion and talked a bit about at the beginning, I think sometimes people argue that to some extent at least, this has already been addressed, let's say in the 90s by people in the nonlinear dynamics community. So
Which part?
well, so for instance, well, it wasn't called combining data assimilation with machine learning, but it was more called like parameter estimation in chaotic systems, and it did involve machine learning techniques at the time, right? And
there's an important difference.
Okay. So I would, let me just finish. So, and also things like estimating Lyapunov exponents from data and so on, right? Yeah, I would just like to hear your answer to
Yes, 2 points.
Yeah.
First, obviously, I know about parameter estimation. I made up a career of it in data simulation, so I totally agree with you. But here, we are not formulating any parametric structure. So it's different than you provide a model, and you then try to estimate those parameters, the parameter of the model using data. Then there is a huge literature on that. And of course, there is a classical state augmentation technique. The same has been done in variational method. There is plenty of people, Michael as well has been working a lot of that. But here is different. We don't take a model at all. We don't have a model at all, or we don't have a parameterization at all. And we only use machine learning to compute a huge amount of parameter. So it's completely different thing, because when you make when you use parameter estimation, data simulation, the amount of parameter you can estimate is very small, because you need the correlation between the observable and that parameter, and that correlation can only be given if the model develops so. So you essentially need a parameter which has a Jacobian with respect to that parameter which is big enough. In this case, you don't do that. You just have an agnostic approach on that, and you plug into methods which are able to deal, because they are run on GPU, with the simultaneous estimation of thousands of parameters. So that data and that W that they use there are thousands of them. Now, regarding the Lyapunov exponent, you are totally right, but we are not trying to estimate the Lyapunov exponent using data. No. I'm just using the spectrum of Lyapunov exponent as a metric to see how close my data-driven model correspond to the original model that I have used in this twin experiment to create data. So I'm not here. I'm not computing the Lyapunov exponent from data. No. I'm computing a model. I'm deriving a model based on data, and then I'm asking which is the spectrum Lyapunov exponent of that model. And there was Michael.
Could I is the next speaker here? I don't know if you want to start setting up, and then we can take one more question. Yes.